So in today's lecture we were talking about direct dark matter searches. We've set the stage for this kind of search in the previous lecture where we discussed various candidates of dark matter. And among the various possibilities to explain dark matter, particle dark matter is specifically very attractive, also because it leads to a rich phenomenology which can be tested in various experiments. The direct search experiments are relying on WIMPs, this is the so-called weakly interacting massive particle, to elastically scatter off standard model particles, for example quarks, and this would lead then to a signature that can be observed or can be used for detection. In other types of searches of WIMP-type dark matter, we would rely upon dark matter to be self-annihilating, which is in some sense guaranteed, given that this is the process which leads to the thermal production of this particle in the first place. Or we could identify at least dark matter candidates in a collider-type experiment where we collide standard model particles to create pairs of, for example, supersymmetric particles. Now, in the case of direct dark matter searches, we need to go through a couple of assumptions to understand the actual signature and the rates that we are able to observe. First one that is most essential, but often enough not really considered in more detail, is the local dark matter density. There's a canonical number of about 0.3 GeV per cubic centimeter, which is determined under the assumption that the galactic rotation curves is tracing out a spherical dark matter particle halo, and then at the solar distance to the galaxy of 8.5 kiloparsecs, the average smoothed out density would be of the order of 0.3 GeV per cubic centimeter. However, there's a number of caveats to this. There's some clumpiness expected, for example. There could be also tidal streams of dark matter, which would enhance or deplete actually the dark matter content that we can see. And so this is not a guaranteed item, but it is the fundamental assumption that's always included, whether it is spelled out or not in any direct dark matter searches. The second assumption is that we would need some elastic scattering to take place to detect dark matter directly. And that is guaranteed, at least in many of the models that are used for WIMP-type dark matter. And in more specific model settings, it's possible to calculate directly the cross-section. And it's usually calculated by looking at these kind of Feynman graphs. So this is a scalar coupling with quarks that I'm considering here, and this leads to spin-independent scattering. And the couplings, of course, are model dependent, but in, as I said, in a rather generic sense, these are calculable. They are tractable, these kind of calculations, and they are then also combined with the more specific type of matter which I use as target material, which then leads to some more specific type of predictions which relate to the structure of the nucleus. Generically, however, it is conceivable that the cross-section is actually the superposition of coherent scattering over all the nucleons of the nucleus. And this leads to a cross-section which scales with the mass number of the nucleus. That's kind of favorable. On another footing, if you have different coupling, so this is for scalar type coupling, but if you have vector and axial vector type coupling, then you expect this coupling to proceed in a spin-dependent way, so that therefore the spin-dependent cross-section scales with the spin of the nucleus, j times j plus 1, so basically spin squared. The overall rate per nucleus is then readily calculated, assuming the dark matter energy density divided by the mass of individual dark matter particles. That gives you the number density of dark matter particles, times the velocity, times the cross-section of scattering. The cross-sections that we are looking at are at the range of about 10 to the minus 45 square centimeters and below, so very small cross-sections. Very naive type of dark matter scattering models where you have a coupling of the WIMP with the Z0, for example, are readily excluded for a long time, and so the cross-section is therefore quite small. The kinematics is simple. It's elastic scattering, and so you expect that the moduli of the momenta in the final state remain unchanged. There's a momentum transfer to the nucleus on which the scattering takes place, which is given by Q. And the recoil energy that is kinetic energy, non-relativistic type because the velocities are small, is given by the q squared over 2 mass of the nucleus. And handing this in the reduced mass of mu, which is simply the product of the mass of the nucleus and the neutrino divided by the sum of the two masses, can be written down like this. And now, then including also the angle theta between the scattering process, you get this kind of recoil energy. And asymptotically, for very light WIMPs, which are much lighter than the nucleus, you get this kind of energy. Whereas when the WIMP has a much larger mass than the nucleus, you get this kind of energy. Typical range of values that you expect here is then of the order of several keV, and this justifies, of course, the non-relativistic treatment. The actual cross-section has to be modified by a form factor, which takes into account the distribution of the nucleons in the nucleus. And this is then giving some dependence on the recoil momentum Q, and the form factor squared goes into the cross-section in such a way that the differential cross-section, the sigma over the recoil energy, goes as the sum of the spin-independent and spin-dependent cross-section times the form factor squared, and each one of these cross-section has its own form factor because the spin-independent relates to the distribution of nucleons, whereas the spin-dependent depends upon the distribution of spin in the system. And then you've got a kinematic prefactor. So this is the differential cross-section per recoil energy. The other assumption, or the other important assumption in this whole game, is then the velocity distribution of the dark matter particles. And the most simple approach is that this follows some kind of Maxwellian distribution with an average velocity of 0. And the velocity is isotropically distributed, so we only care about the velocity here, not the vector of velocity. And the dispersion that goes into this is related to the circular velocity that we observe, that is the circular velocity of the Sun around the galactic center, by a factor of square root 3/2. There is a maximum energy of this distribution where this is truncated, so this doesn't go to infinity, because once the velocity is beyond the escape velocity, the number of dark matter particles at these velocities will be suppressed because they will gradually escape from the gravitational potential. So taking everything together, we get the differential rate, and that's then simply the integration over the velocity distribution, velocity times the cross-section, and the prefactor is the number density of the dark matter, and it's 1 over the nucleus, which comes from the momentum transfer. Now, taking this to more quantitative level, I've got here a plot which shows the actual rate, so this differential rate, in units of events per kilogram per day per keV as a function of recoil energy. So this starts at 0 keV and goes up to 80 keV, and then it would continue, of course. However, you see that with increasing values of Q, the rate drops very rapidly. So this is a logarithmical scale, and these are 2 orders of magnitude 4 and 6 orders of magnitude. And this is now plotted for various target nuclei of various mass. So we've got sodium down here. This is the gray line, which is the smallest nuclei. So therefore, also form factors do not suppress so strongly. And it is also the one which has the smallest scattering rate. And there you see the scaling of A squared kicking in. So if you compare that with, for example, tungsten, you find almost a factor of 100 higher scattering rate, which relates, of course, to the mass squared ratio of tungsten to sodium. For tungsten, however, the form factor kicks in and reduces the scattering cross-sectional scattering rate considerably. And then you've got, again, a rise over here, but albeit with a much smaller scattering rate. For a noble gas like xenon, here's given as an example the number of events that you would get after integrating over all the recoil energy. And then this rate above a threshold of about 10 keV would be the order of 20 events per 100 kilograms per year. This is, of course, taking into account more specific mass and a specific spin-independent cross-section of 10 to the minus 45 square centimeters. So you can basically scale that number. If you have 10 to the minus 47, then you end up with the order of 0.2 events per 100 kilograms. Now, the effect of the mass is demonstrated in this figure, and also the effect of the form factor. So for 100 GeV mass and no form factor, this differential scattering rate on tungsten would look like this green short dashed curve. Including the form factor, you see that this modifies the rate considerably and brings it down to a very small value. And finally, if you reduce the mass to 25 GeV, you end up with this long dashed line, which tells you that the rate increases. But for typical thresholds of 10 keV or so, there's not much to be gained. So the rate really becomes smaller and smaller and smaller for most thresholds if you reduce the mass. Now the major challenge is, of course, you need to detect this kind of faint signal against the background of, for example, radioactive decays and also nuclear recoil type events which come from neutron scattering. Now let's have a look at the background contributions. Just as a numerical example, consider a normal human body or human tissue. There is a considerable amount of potassium-40 in our system, and potassium-40 leads to an overall activity of about 50 becquerel per kilogram. Now, taking the same kind of units, that is the number of decays per year per 100 kilograms, you end up with a value of a whooping 2 times 10 to the 11 decays per 100 kilograms per year. And this tells you how much it is important to have radiopure elements and also to not contaminate any kind of detector by, for example, radio impure material. That's why whenever you see people working with these kind of detectors, they wear typically lots of protective gear, not to protect themselves, but to protect the detector against contamination. And radiopurity is not only an issue about getting rid of the isotopes which are maybe naturally abundant, but also to avoid activation. And specifically for shielding, it's very important to choose material which is radiopure and has not been activated recently. And one example is that it's been lead has been used from Roman ships which were sunk and have been resting for about 2,000 years at the bottom of the Mediterranean. And this is very low in 210 lead, which otherwise is rather high when you have freshly mined lead. And this decays away over that time and can then be used in a much better way for the shielding of these kind of instruments. In terms of cosmic rays, the most problematic particles are the muons because they're deeply penetrating. They can be observed very low, deep in the underground. And there's no way that you can do this shielding. You have to rely on natural shielding. And that's why these laboratories are usually run in deep mine shafts where the rock overburden shields away the muons. And this is shown here in this figure, where you see the muon intensity in units per square meter per year, how it is dropping over 6-7 orders of magnitude when you go from something close to the surface down to very deep mines, which have a depth such that the water equivalent overburden is of the order of 6,000 meters. And in that case, the rate drops to values which are about 100 or so per square meters per year, which makes it possible to deal with this background in a sense that using a simple scintillator is possible to detect the muons passing through, and then the detector is usually vetoed for any subsequent events because they could be caused by neutrons which have been generated by these muons. And then there's finally also radon, which is a major issue and needs to be purified so that it is flushed out of the system. And the values that are reached now in, for example, xenon detectors is at the level of a few microbecquerel per kilogram. And finally, there's the background of solar neutrinos, which are essentially indistinguishable from the WIMP scattering. However, the neutrinos are, of course, interesting by themselves, and there's a possibility to distinguish them because the neutrinos, of course, come from the direction of the sun. However, there's also the case of diffuse neutrinos coming from supernova explosions, and these are indistinguishable. And this becomes an issue. Now, detection principle, how to do it. This is really the art of the whole thing. So the aim is to get a 10 keV recoiling nucleus and detect it and get rid of most of the background. And there's two channels which are used. The one is the ionization, the other one is phonons, or heat, effectively. In the case of ionization, in principle, there's this canonical way of detecting scintillation light, that comes out of active material, like sodium iodine or even liquid xenon. And then the light is registered, for example, with PMT. So this is a separate target material and also light-producing material, and then you need separate from that photon detectors. In the case of semiconductor materials, the most simple case is a diode where the reverse bias voltage is used to deplete a larger volume of this material so that electron hole pairs can be detected and can be collected in electrodes which are integrated and then are registered as charge, for example, in the system. In the case of phonons, the case can be made for solid-state detectors, that is a crystal lattice, that the phonons become observable. And this requires, however, to bring down the system to millikelvin temperatures. And that's kind of a challenge. In this case, the phonon detection is done in cases like where a transition edge sensor is used by having thin tungsten films on top of the material so that the phonons can be converted into a measurable signal. And that's done in a very genius way because a transition edge sensor is operated at the transition between superconducting and normal conducting, and that's a very sharp transition. And the moment that there's some phonons dissipating some heat in the system, a thin film will warm up and becomes normal conducting, and that leads to a measurable signal in a properly set up circuit. And then the system will register the phonons in such a system. It works essentially like a thermometer. Another way of detecting the energy dissipated in form of heat is to have a superheated fluid, which, when elastic scattering takes place, leads to the formation of bubbles. And these bubbles can be observed, for example, with a simple camera, with a CCD camera. And this is a very, very much, a very interesting way of detecting nuclear recoil, because the gamma background really doesn't matter here. This is something which is working only very efficiently with nuclear recoil. And besides the imaging, there's also the possibility to measure the acoustic effects in the liquid, which lead to some acoustic waves when the bubble collapses that can be used. The key to a successful operation is not only the active suppression of backgrounds coming from the outside and control of the radio purity of the setup. It's also important to make sure that the beta and gamma signatures can be separated from the nuclear recoil. And that's done in most of the cases of the detectors, and we'll see two examples in a moment, by combining the ionization and the phonon type of signal. Because the phonons are generated more efficiently in the case of nuclear recoil, whereas ionization is produced a lot or a stronger signal is produced in that channel in the case of electron recoil, as it is the case for beta and gamma decays. For the neutron events which are leading to a nuclear recoil event as well, it's important to have sufficiently large detector volume, so that the big difference between the neutron and the WIMP scattering is the WIMP scatters only once and then it leaves the detector volume, whereas the neutron can scatter multiple times and deposit energy more than once because of the larger cross-section. And neutrons induced by muons can be, of course, suppressed by making sure that there's a good muon shield or muon veto in place. However, if you take all the precautions and then you end up with some excess events in your signal region, in your detector in the end, it's quite a challenge to make sure that this is really dark matter related and not something which is an unknown or underestimated background. Because contrary to other measurements, like consider a collider, if you don't have a beam operating, you will not have any events. Or you could even change the energy and do all kinds of nice things to check that your signal is real. In the case of a direct dark matter search experiment, you cannot switch off the dark matter particles. So they will always lead to signal. So you don't have a real chance to measure the background independently. However, there's a couple of approaches that can be used. And one of them is annular modulation. And that is something which comes from the fact that the sun moves around the galactic center. the Earth moves around the Sun. And in the summertime, in June, Earth velocity and Sun velocity superpose in a productive way, so that leads to a larger velocity in the galactic halo, whereas in December, the velocities subtract from each other, so the average velocity is smaller. And the effect is, in the end, that there's a modulation of the rate with a yearly modulation. That's roughly the relative modulation corresponds to the relative velocity difference, and relative velocity difference related to the total velocity, and that's a few percent. And in principle, this can be detected, but keep in mind, if you have only a handful of events per year, it's kind of a difficult thing to do. Either you have to run for a very long time to detect it, or you need a larger volume to increase the rate. There's another cross-check that can be done, which is characteristic for the WIMP scattering. Because they are so slow, the effect of the coherent scattering A squared depends upon A squared and J squared, as we said, for spin-independent and for spin-dependent scattering. And in case you have several detectors which use different materials, you can cross-check on that. So if you have, for example, the spin-dependent signal, you can use with germanium detector, which doesn't have a spin. It should not show up. Otherwise, there's some effect which is background related. And also some of the dependencies are characteristics. So this is really a cross-check that can be performed to rule out that this is something which is background. And then finally, it's in principle possible to measure the direction of the WIMPs, and there should be a signal which is stronger in the direction in which the Sun moves. So there should be a dipole anisotropy in the WIMP arrival distribution. And that could also be measured. However, it's again the same problem. In order to measure this with some accuracy, the number of events that need to be detected is so large that this is difficult to do. Also, at the same time, the threshold for measuring the direction is larger than for a detector which is not trying to measure the direction. And that means that the rate drops even more. So this is really difficult to pull off, but maybe this is also a chance to distinguish from the neutrino background. Now let's look at some particular example of this kind of detector. So first we look at something which I call a cryogenic detector. So that's a detector which is operated at a temperature below 100 millikelvin. So this is really something which requires a lot of technology to get down to this temperature. And it's not only a small detector, these detectors are reaching several kilograms of mass. So in the SuperCDMS, which is operated in the Sudan mine, they are using, for example, germanium detectors, among others. And the germanium detectors are shaped in this way. This is a disk of high or ultra pure germanium 74. They are 76 millimeters in diameter or 25 millimeters thickness, so roughly 3 inch by 1 inch. And the mass of such a germanium disk is 0.6 kilograms. The detector has the integrated electrodes. You see here on top, there's 3 segments, the segmented electrodes and a guard ring electrode. You see it in the SketchUp here. It's combined in a clever way, so the top and the bottom electrodes in such a way that it's possible to measure the spatial position of the scattering event. And on top of this is mounted a set of transition edge sensors which detect the phonon signal. So this allows then a better separation of ionization events, that is events which come from beta or gamma, and nuclear recoil events. Now, the segmentation of the electrodes has the big advantage that it's possible to veto events which have been produced at the outer edge of this detector. So that's usually discarded because they cannot be characterized so well. And the way that the electric field is shaped with these electrodes is such that the scattering, when it takes place in the bulk of the detector, so this is the top and this is the bottom part of this disk. So this would lead to, if scattering takes place here, by the way that the electrodes are shaped, the electron and hole pairs, they will just move to the electrodes on the top side, and they will not lead to a signal on the bottom part. If it happens in the bulk, then the drift will go in the direction because of the way that the field is shaped, and then you have a signal which is registered in both cases. And the phonons are registered with the transition set sensors, and the way such an event would look like a vanilla type nuclear recoil event is you have the incoming particle, it scatters, it produces phonons, and it produces charge. The charge is drifting upwards and downwards. It will be registered by the electrodes, and the phonons will lead to a signal in the transition edge sensors. Additionally, there's also timing signal, which allows to separate surface events, and the electrodes allow, the guide electrode on the outside allows to discard surface events or events which happen on the outside of this detector. Now, the separation works in such a way that you can measure for each particle the ionization yield. So that's the amount of charge that is being produced in the scattering. And you can measure as well the phonon component of the scattering event. And in a two-dimensional plot, you can make out two distinct bands. And in this case, the bands are populated by calibration sources. So the detector is exposed by gamma source, 133 barium. And this leads to the blue events, which you see populates mainly the part of this plane where the ionization yield is large. And also the phonon recoil energy is quite large, because there's also phonons produced. As you see here, there's some phonons even produced when the charges are traveling to the electrodes. But you can also make out that most of the events are sitting over here with maybe 100 keV phonon recoil energy and an ionization yield which is shifted to be unity. That's per definition the value that you get for gamma ray type events. Now, to check where the nuclear recoil events happen, a calibration source was used, Californium, which is a neutron source, the way it is set up. And there you see now the green events, and they fall at a range of about 30% of the ionization yield. And the phonon recoil energy is centered to smaller values. There's some tail over to larger values, but most of the events fall down in this band here. And you can clearly make out that there's, of course, also some spillover, so they're not completely separated. But there's a very good distinction between the two types of events possible by the combination of phonon and charge that is produced. So this is then combining several of these disks in layers or in stacks and towers, they're called. And then this is put in a dilution type refrigerator, which can cool them down to below 100 millikelvin. And then they're operated for years, or year time, to sort of and collecting then events. Now, another type of detector which relies on a completely different material is xenon. So xenon can be cooled down to produce liquid xenon well below 100 Kelvin. So it's not millikelvin, but it's tens of Kelvin that you need to cool it down to. So it's more comfortable and easy to do. And in such a vessel, then you can maintain a dual phase type detector. So you have a liquid phase, which is the white part of this detector, and a gaseous phase, which is the part above. The tank has on the bottom an array of photomultipliers, on the top an array of photomultipliers. And the whole tank is then so there's electrodes set up so that the whole tank is they're set up a drift field. And the events of a nuclear recoil would proceed the following way. So there would be a scattering recoil event, and this only few electrons are produced. They would drift up. The xenon would produce light that would be picked up by the PMTs. The drifting electrons would at some point emerge out of the liquid phase and move into the gaseous phase, where an anode wires are used to increase the electrons so that they produce a stronger signal. This is collected also in the anodes, and then light is collected in the photomultipliers on the top arrays. And the advantage is now that by measuring the light and also measuring it in this segmented way, it's possible to determine the position where the light is emitted by looking at the pattern of the light which is recorded. And this allows them to calculate or reconstruct the XY position in the plane here. Through the time of the drift of the electrons in the constant electric field, it's then possible to determine the depth where this scattering took place. So this acts like a three-dimensional reconstruction. This is often called the time projection chamber. And the characteristic signal strength of the S1 and the S2 can be used to distinguish between nuclear recoil and electron recoil. In the nuclear recoil, the signal that is produced in the S2 is not as strong as in the case of an electron recoil or beta gamma event. And this can be used to distinguish. For a neutron, you will have multiple scatterings, and this will lead to electrons which can be then drifting upwards, and they would lead to different times of arrival, or also the pattern would be looking different. So this can be used to distinguish this. So there's a number of observables, so amplitude, the time difference, that can be used to distinguish. And the reconstruction in spatial coordinates is very important to get rid of the events which are produced at the edges and which are very likely background events. Here's some details of the detector. So this is the tank. It's about 90 centimeters in diameter, and it is equipped with electrodes which shape the electric field so that you've got a nice constant electric field. So these are the field lines which thread through the detector. And you see the field is very strong over here when you start going out in the vicinity of the anode. And then here's the breakdown of the various backgrounds. This is important because this is basically summarizing what we've been discussing in a very nice and concise way. So the radon activity of 10 microbecquerel per kilogram leads to a total rate of 620 events per ton per year. So that's the units for the rates here. That's electron recoil event. The solar neutrinos, also electron recoil events, they will be producing 36 events per ton per year. And then there's some krypton, which comes from the mostly from the nuclear bomb tests. That's leading to 31 events per ton per year. And this is a quite interesting background. So this is a double beta decay of 136 xenon, which leads to 9 events. And then there is some material radioactivity, which still leads to 30 events. So the bulk is really the radon, which is producing electron recoils. But electron recoils can be distinguished because of the fact that electron recoils will lead to a stronger S2 in relation to the S1 event. The nuclear recoil type background is really tiny. So there is some neutrons produced by muons. So these are the radiogenic neutrons. They lead to, radiogenic neutrons are neutrons which are coming from radioactive decays in the end. So this is like 0.55. The muon-induced neutrons can be discarded because the whole thing is embedded into a water Cherenkov tank. So that leads to suppression that's really, really efficient. And then there is some other neutrinos which are again leading to some nuclear recoil events of 0.6 or so. So this can then be used to operate such a detector and discard the events and reject background efficiently. And the result was reported. The result of the first year of operation of the 1-ton xenon detector in the Gran Sasso was operated just a few years ago. So 1 ton year, or in the end 278 days of operation, leads in an energy range above about a few keV as the nuclear recoil energy. So this is the efficiency as a function of the recoil energy. And you see that most of the events would fall here between 5 and maybe 50 kiloelectron volts. And if you compare that with the recoil spectrum of the WIMPs, this is the 200 GeV, this is the 50 GeV, and the 10 GeV, you clearly see that the best sensitivity is reached at about 100 GeV or so. And so this is the result. I just want to go through some of this before we look at the final table. So this is now plotting the actual reconstructed positions projected now in the XY plane. So that's transversal to the cylinder axis. And there you see this is the outer edge of the triumph projection chamber. The little gray dots, these are all individual events which are not observed in the fiducial volume, so they are outside. So they are rejected anyway. And also these ones are, even though they seem to be falling in the XY plane, they are still outside the valid range of Z coordinates. So this is on the right side, so this is now basically a cut orthogonal to this one. So this is the depth of the vessel, so the black is the TPC, and this is the radius, now in squared, so this emphasizes the volume that you are looking at. And you see that all the gray stuff is discarded, because this is just surface events or events near the edge. And now the events are selected according to their type of event characteristics. So the black ones are, for example, electron recoil, that can be identified as electron recoil. And for some of these events, you just see a few of them. There's like this one, this one, this one, this one, and these few. It's possible then, because they pass all the cuts, to look in a little more detail. What is the likelihood that these are coming from either surface, neutron, electron recoil, or even accidental coincidence, or WIMP? So this is color-coded in these little pie charts. So this event here, for example, is for 50% probability, it's a neutron-type event, but it has some probability to be also a WIMP-like event. It's got a little accidental coincidence probability, and it's got some probability to be just a surface event. And you can also see that this event here, for example, is within the blue circle. The blue circle is the 0.9 ton type cut that has been done to select events which are far away from the surface, from the outside of the TPC. And this one can be seen as happening down here. So this is really close to this 1.3 ton range. So it's quite kind of a low converting event, but it's got some probability. It passes the cuts. And then you've got this event here, which corresponds to this event over here, which is just outside of this blue circle. And so you would count that there's one event here, and then you've got another one over here, which has a sizable probability to be a non-WIMP, to be sort of a non-electron recoil event. A different way to look at these is through the strength of the signal, and this is shown here. So this is the CS2, this is the corrected S2 signal, and this is the corrected S1 signal in photoelectrons. And the a priori chosen signal region is this red band here, which would be the the nuclear recoil part. And you see that the electron recoils are lying over here, and this is indicating the energy of the recoil event. So this would be kV of the nuclear recoil. And you find that there's in the end there's only two events, this one I believe and this one, which fulfill all the cuts and have a sizable WIMP contribution. Or maybe it's this one and this one. I think these two are the ones which are left after all. So the final result of this thing, let's have a look at the 0.9 ton column here, is now giving the breakdown of all the events. So the data is two events which were detected, which fulfill all the criteria and are within the 0.9 ton fiducial volume. And the breakdown is that the total background, which is left after all the cuts, is 1.6 events. So most of them are just electron recoil events. And there's a best fit WIMP event of 1.16 in this. So since this is not necessarily unity or 2 or 3, this is basically the probability to detect a certain number of events. Whether you assign the one or the other event is just a statistical decision that you want to take. So this is adding up to about 2 events which we detect. So there's a little difference. So this 1.6 plus 1.16 would be 2.7, but this is all consistent with the expectation. So there's no excess observed. And so this best fit value is found for a cross section of 4.7 times 10 to the minus 47 square centimeters. So that would be the best fitting result. And ultimately then these kind of observations are turned into limits. That is, limits that can be statistically excluded. And the limits are reported typically in the dark matter nucleon cross section. And you see here that the Xenon value is because this is now the nucleon cross section and not the nucleus cross section. So this is the cross section that's been ruled out. And you see that this is getting now to a value which is rather close to this solar neutrino background, and ultimately down here 10 to the 49 or so, you get down to the value of the diffuse supernova background. To summarize and conclude on the direct search methods, there's a couple of ways which are considered to move forward. One is straightforward: make the detectors bigger and run them longer. You see that running longer is not really such a good solution anymore, because sensitivity now grows with the square root of the time because the background is already dominating. However, if you make the detectors bigger, you basically increase the volume substantially, and you can get rid of more background actually. So this is helping quite a lot, and the current, let's say, major proposal that's already moving ahead is the Xenon N-ton, so that'll be making this detector bigger essentially and improving gradually on a few of the features. And they have the potential to really go down to the neutrino floor. There's a slightly different direction that has been now pursued, and that is to try to fill this part. So you see here there's lots of empty space which has not been explored. This is not really the favorite region of dark matter mass, because this would be a very light dark matter particle. But nevertheless, there's some proposals that you could have dark matter in the right relic abundance also in this regime. And this is being explored right now to reduce the threshold. And the best way to reduce the threshold is to move away from the xenon type detectors and go towards detectors which have a lower intrinsic threshold, like for example germanium or silicon detectors. So there you can push down the threshold, and the record I think is right now at 20 electron volts or 30 electron volts threshold. And finally, there's also the interesting point about searches that try to look for electron recoil. There you have, of course, more background. But there's some interesting possibilities to detect maybe other types of dark matter through electron recoil. And there's currently a heated debate ongoing about an excess that was observed with Xenon 1 ton, which, however, is still within, let's say, the error budget of this 2 beta decay of 136 xenon, which could explain that excess actually. And there's some additional ideas to go into a more exploratory regime, that is, go between to sub-GeV dark matter searches, which would require a different technique, and also to try to work towards detectors which can also determine the direction to reduce the impact of solar neutrinos.